Hi guys, Ms. Francis here. Today I'm going to talk to you about the chi-square test. Chi-square test is another statistical tool similar to standard deviation that scientists use to measure their data. They use it to determine whether any deviation from what is expected within their experiment is significantly different from the deviation within their data that just might happen because of chance. So this is our formula. Chi-squared is equal to the sum of the deviation from the expected value squared divided by the expected values. So here just means the sum of our values. D squared, that's the difference of our observed minus our expected values, and E, that's our expected values. So what does that mean? Well, let me give you an example. Suppose I have a penny and I am flipping it 10 times. So I would expect 5 heads and 5 tails, right? Unless my coin is weighted. Well, let's say I get 6 heads and 4 tails. I can't really tell if I just got 6 heads and 4 tails because of chance, or if because my penny was weighted. Furthermore, that's a really small sample size. So let me take another example. Let's say I flip it 200 times. And now let's say I get 110 heads and 90 tails. Well, do I think that my coin might be weighted? Not really, but am I sure? What if I got 130 heads and 70 tails? Or what if I got 150 heads and 50 tails? Or what about if I got 199 heads and only 1 tail? Well, then I might start to think, yeah, the coin must be weighted, but am I really sure that the coin is weighted? No, because that could still have happened due to chance. Well, this is where the chi-square test comes into play. It's going to help us determine whether I got 199 heads and only 1 tail because of chance, or if because my penny actually is weighted. So let's try a sample problem. Let's see. This is the flipping of the coin. So we collect data by flipping the coin 200 times. The coin landed heads up 108 times and tails up 92 times. So my observed is heads is 108, tails is 92, for a total of 200. But my expected, I'm going to expect to get 100 heads and 100 tails, right? Because there's a 50-50 shot of getting heads over tails. Then I need to find the difference and take the difference squared. Before I do that, though, I need to establish the null hypothesis. And in this case, my null hypothesis is that the coin is not weighted. Therefore, I should have equal chance of landing on heads or tails each time. So we would expect 100 heads and 100 tails. So we'll put this information into a table, and then we start to figure out the difference squared, the difference squared divided by the expected, and then we add everything up. So the difference here is 8, the difference here is 8. Squared, 64, 64. And it's not always going to be that our difference squared is the same number. In this case, it just happens to work out that way. So now we would take 64 and divide it by 100. Here we would take 64 and divide it by 100. So we would get 0.64, and we would get 0.64. But now we have to take the sum of those results, and what we end up with is 1.2. That is our chi-squared value. But it's not enough to just stop here. Let me show you what we're going to need to do next. So now we look at our chi-square value and we compare it to the table value. This is what I mean by a table value. This is on your reference tables. In science, we always use a p-value of 0.05. So we're going to be looking at this column. And we need to determine something called our degrees of freedom, where our degrees of freedom are the number of phenotypes minus 1. So in this case, we had heads, or we had the possibility of getting tails. So our phenotypes are 2 minus 1. So our degrees of freedom would be 1. You guys get points for writing down our p-value is 0.05, and you get points for writing down your degrees of freedom. So make sure you indicate that. So what that helps us figure out is our critical value. So for us, our critical value, or CR, is 3.84. So why is that important? Because it's going to help us determine whether or not our data is statistically significantly different, meaning that our deviation from our expected results are not, or maybe they are, just due to chance. So if the chi-square value is less than the table value, it means that there's no significant difference between the observed and the expected values. In other words, any deviation between our experimental results and our predicted results were just due to chance. But if the chi-square value is greater than the table value, that means that there is a significant difference between the observed and expected values, and something other than chance is going on. So we need to figure it out. We have some explaining to do. So in the example of our heads and tails, our chi-squared value was 1.2. 1.2 is less than our critical value of 3.84. So in our case, the reason why we got 108 heads and 92 tails was just due to chance. However, if for some chance, let's say our chi-square value was greater than the table value, then that would have meant that our results are due to something other than chance, and maybe in fact the coin was weighted, and that's why we ended up with the values that we ended up with. So how do we explain what this means? So our null hypothesis was that our coin is not weighted. We are going to accept that null hypothesis because there is no statistically significant difference between our expected and our observed values. That's because our chi-square value was smaller than our critical value. So that means that any difference between our expected and observed values are just due to chance. So how did that apply to our experiment? The coin was not weighted. However, if our chi-squared value was bigger than our critical value, then there is a statistically significant difference between our expected and observed values, and that any difference between our expected and observed values are due to more than just chance. So we need to account for those differences and explain how it applies to our experiment. Well, in the case of the coins, that means that the coins must have been weighted. So let's try another example. Suppose that the ratio of male to female students in the science faculty is exactly 1:1. But in the AP Bio class over the past 10 years, there have been 80 females and 40 males. Is this a significant departure from expectation? So we make our chart and we fill it out. So our observed numbers are that we have 80 females and 40 males for a total of 120. However, we expect a 1:1 ratio. So we expect 60 females to 60 males for a total of 120. We find the difference between our observed and our expected. We square them, and then we take that squared number and divide it by the expected. We add those numbers together to give us our chi-square value. And in this case, how many degrees of freedom do we have? That's right, 1, because we have male and female. So that's 2 categories minus 1 equals 1. So our degrees of freedom are 1, and our p-value is 0.05. That means that our critical value is equal to 3.84. In this case, our chi-squared value is greater than our critical value. So what does that mean? Well, that means that we are going to reject our null hypothesis. And our null hypothesis was that it's not a significant departure from expectation. So yeah, there is a statistically significant difference between expected and observed values, and that these differences are due to more than just chance. So we have to figure out how to account for those differences and explain how it applies to your experiment. So I don't know, maybe the population has changed and we have more females in the population than males, and that's why there are more females than males. But let's see how it would apply, the chi-square test would apply to our animal behavior lab. So let's say we wanted to see if there was a preference of brine shrimp to hot and cold environments. So our null hypothesis would be that there was no preference. And our degrees of freedom would be 1. How did I get that? Because I have hot or cold as my categories. So my categories are 2, right? Hot or cold, minus 1 is going to give me 1. And we remember that our p-value is 0.5. We know that our critical value, oops, I keep on putting CR. Our critical value is 3.84. So we would go through, after 20 minutes, the clip closed off at the 2 end. 30 were found at the cold side and 10 were found on the warm side. So 10 were found on the warm side, 30 were found on the cold side, for a total of 40. Well, if we expected no preference, then we would expect 20 on each side, for a total of 10, 10, 100, 100, 100 divided by 20, 100 divided by 20, what is that? So that's 5, and that's 5. We add these together to equal 10, which is our chi-squared value. But wait, we're not done. We have to explain what that means. So our chi-squared value is greater than our critical value. So what does that mean? If our chi-square value is greater than our critical value, that means that we're going to reject our null hypothesis. In this case, our null hypothesis was that there was no preference. So instead, we know that there is a statistically significant difference between the expected and observed values, and that's because there is a preference of pill bugs, or brine shrimp, to one temperature over the other temperature.